Okay, so I'd like to talk about some work I've been doing recently with Robert Digraph, Edward Witten, and Masahito Yamazaki. And it started as a project I did a couple of years ago, but now we're pursuing it a lot more recently, doing a lot more things. So I'd like to start by reminding people about, which is probably a familiar story, about integrable spin systems. This is a story developed by Baxter and Yang and Onsager and others. So we're going to consider a two-dimensional lattice, and the links of the lattice will be labeled by spins, as shown. And at the vertices of the lattice, we will have an interaction between the spins, like a Boltzmann weight, which depends on the spectral parameter Z. So from this data, one can construct in a standard way the transfer matrix, seen in this diagram. It's obtained by multiplying this, the Boltzmann weights are into what's called the OR matrix. We multiply the OR matrix on various adjacent sites and then take the trace. The partition function is again defined in the standard way. We sum over all spin configurations, take a product over all vertices of the Boltzmann weights, and one can check this is the same as the trace of the nth power of the transfer matrix. Now, so far this is very general. It describes any two-dimensional lattice model. But what's special about the models we're going to consider is the integrability. And that can be expressed by saying that the transfer matrices for two different values of z commute with each other. And this follows from the Yang-Baxter equation for this OR matrix, or z. Now, there are some very famous examples of integrable spin systems of this type. If the spectral parameter lives in the complex line, this an example is given by the XXX model, also known as the zero field 6 vertex model. If the spectral parameter lives in C star, what we find is the general 6 vertex model, or the XXZ model. These are equivalent. Just a reformulation of each other. And if the spectral parameter lives in an elliptic curve, the model is, we find the 8 vertex model, or the XYZ spin chain. So the question we're going to try to answer in this talk is, where do these spin systems come from, and why are they integrable? Now this question, I think, was first posed by Edward Witten in a 1989 paper. And he solved a special case of this. Suppose we consider this model with spectral parameter in C star, and then take the limit when the spectral parameter goes to infinity. What you're left with is an integral model with no spectral parameter. And what Witten showed is that this model arises by studying Wilson lines in Chern-Simons theory. The OR matrix is the OR matrix which gives the Witten Ricciuti triav invariance of knots. So the goal of this talk is to generalize this story to a version where one can see the spectral parameter. So we'll introduce a four-dimensional cousin of Chern-Simons theory. And in this four-dimensional theory, we'll see that Wilson lines, just like in Chern-Simons theory, Wilson lines will lead to integrable spin systems. But the extra dimension will allow us to see the spectral parameter. Now, I'd also like to talk about some new work we've been doing very recently, which is that one can also see from this four-dimensional theory why certain two-dimensional sigma models on homogeneous spaces are integrable. We'll embed these sigma models as surface operators in this four-dimensional theory. So let me describe the four-dimensional theory. It's very simple. It's not Lorentz invariant, so we'll write the spacetime in which it lives as R2 times C. The gauge field, instead of being a standard gauge field, only has 3 components. There is no Z component of the gauge field. The action, we just take the usual Chern-Simons action, but now we multiply it by dz so that we can integrate it over a four-dimensional spacetime. the gauge symmetries are the usual gauge symmetries. Now, if one varies the gauge field A, one finds the equations of motion, which tell us that in the xy plane, the connection is flat. In the z plane, we have a holomorphic, we have a d bar operator, and then there's a compatibility between that holomorphic connection and the connection in the xy plane, which is expressed by these two equations. Now, the resulting theory is it's a mixture of a topological theory and a holomorphic theory. So in the xy plane, it's topological, and the z plane is holomorphic, meaning that expectation values of operators will be holomorphic functions of z. And what will be important for us is that there are Wilson lines in the xy plane. We can draw a line in the xy plane, do the usual holonomy of a connection in that line, and that will define an extended operator. So our goal is to use these Wilson lines to understand the integrable spin systems such as the XXX or XXZ spin systems. So the simplest case is we'll consider our theory on R2 times C and with gauge group SU2. And we'll draw two crossing Wilson lines like we've shown. Now these Wilson lines, we're going to take the plane on which we've projected as the XY topological plane, and they cross in that plane, but they're separated. They're at different points in the complex plane Z. So this is at point Z, and this is at a point W in the complex plane. Now, at the end of these Wilson lines, there is a space of states, which is just C2. And if I take a state at the end of a state here and a state here, and I bring them up, as they cross in the middle, these states exchange a bunch of gluons. And then they come off again, and I get some new states at the other end. So that way, with this exchange of gluons, it gives us a linear map from C2 tensor C2 to C2 tensor C2, which depends on a parameter Z minus W. It depends on the distance between these guys. So the main theorem from which everything else will follow is that this linear map arranged by exchange of gluons is the OR matrix for the 6-vertex model. And the spectral parameter is the distance between the positions of the Wilson lines in the Z plane. Okay. Now you might think that computing this, here we have some gauge theory, and we're going to exchange the diagrams for the exchange of gluon can be very complicated, and it will be hard to compute this exactly. So I'll explain in a little while how to do this computation. But before I do that, I want to explain how we can see other aspects of integral models from this point of view. So first, let's see, why does this exchange of gluons lead to the Yang-Baxter equation? Well, that's very simple. The Yang-Baxter equation concerns the composition of 3 of these operators in 2 different ways. And as we see from this diagram, if we have 3 Wilson lines which cross, as shown, we can use topological invariance to move this blue Wilson line over to the other side. And that leads to an equation on this OR matrix. And that equation just is the Yang-Baxter equation. So just like, in the same way as the Yang-Baxter equation studied by Reshtik and Turayev arises from topological invariance of Wilson lines in Chern-Simons theory, the Yang-Baxter equation with spectral parameter arises from topological invariance in this 4-dimensional theory. So what else can we see? One can ask how the transfer matrix arises. So to see this, we'll put our theory on OR cross S1 cross C, so the topological direction has a circle, and have a bunch of Wilson lines in the OR direction. Then at the end of these Wilson lines, we have a space of states, which is C2 for each Wilson line. So we tensor them all together to get n copies of C2, and that's nothing but the Hilbert space of the spin system. How do we see the transfer matrix? We add another Wilson line orthogonal to those wrapping the circle. And this gives the transfer matrix. The reason why is that when this Wilson line crosses each of those guys, we get the OR matrix. And as I move them along, I just take products of OR matrices. Because it's a circle, I take a trace. So that's kind of evident that this is the transfer matrix. Well, one can see why transfer matrices commute. That's very simple. If I have two such Wilson lines, one at W and one at W prime, I can slide one, oops, these pictures weren't meant to jump. I can slide one past the other just by topological invariance. Because one can do this because the theory is topological in the xy plane, and because W and W prime are different, these Wilson lines don't intersect. So we can just move them up and down. And the partition function of the theory, well, it's pretty obviously is just the expectation value of a bunch of Wilson lines arranged in a lattice on the torus. Okay, so far we've seen how all the main features of integrable spin systems, like the Yang-Baxter equation and the fact that transfer matrices commute, follow in a very simple and formal fashion from the fact that this theory is topological in two directions and holomorphic in one complex direction. So what I'd like to explain next is how do we know that the OR matrix we get from the crossing of Wilson lines really is the OR matrix of the XXX model? Well, to do this, you notice that the OR matrix of the XXX model has an expansion in terms of a parameter, which will be the loop expansion parameter of the gauge theory. And the leading term is just the Casimir of my Lie algebra divided by Z minus W. And then there's higher terms. And some results of Drinfeld tell us that this property, together with the Yang-Baxter equation, fixes this OR matrix uniquely. It's a very rigid object. So what we have to do to check we really find this OR matrix is first we calculate the exchange of a single gluon, and then we use the Yang-Baxter equation to say, well, the rest of the terms are determined. So this is kind of like the bootstrap method, but the bootstrap method, you might calculate some simple OPE and then use consistency, associativity of the OPE to determine more complicated correlation functions. Here, we're using the version of the bootstrap method, but for Wilson lines instead of for local operators. So let me sketch the simple computation which tells us that the exchange of a single gluon looks like this. So what we do is remember our gauge theory, there's only a 3-component gauge field. So we'll choose a gauge where the gauge looks like this, and then you can just write down the propagator in this gauge, and you can ask, what is the gauge field sourced by this vertical Wilson line? If you calculate it, if you were doing ordinary Yang-Mills theory, this would be, electrostatics, and there would be one over OR decay. Here one finds there's an extra, because it's a first-order theory, there's an extra derivative of Z, so we find the gauge field it sources looks like this. Now, if you integrate this gauge field over this curved Wilson line, well, because this gauge field has a dx in it, it will be 0 when I restrict it to the vertical components. So the integral only gets contributions from the horizontal components. And if you calculate the integral, you find up to factors of 2 and pi, it's 1 over z. So this is why the exchange of a single gluon leads to the Casimir times 1 over the distance. Of course, this story can be generalized. If we replace C by some other Riemann surface with a Noor-vanishing holomorphic 1 form, we will find other spin systems. So the XXZ spin chain arises if I put the theory on R2 times C star, and the XYZ spin chain arises when I put the theory on an elliptic curve. But there's some subtlety. There we need to use, we work in a background with a non-trivial SO3 bundle, with a rigid SO3 bundle. And to see more general models, we'll just use some other gauge group and some other representations as the Wilson line. And this sees a wide variety of spin systems. So my personal conviction is every aspect of these two-dimensional spin chain systems can be understood in terms of this four-dimensional theory, firstly. And secondly, every occurrence of these two-dimensional spin systems in other areas of physics can optimistically be understood by various dualities in terms of this four-dimensional theory. This is an ambitious goal, but I'd like to explain one aspect of this for the rest of the talk. So it's understood, it's known that continuum limits of these two-dimensional lattice models can be described in terms of two-dimensional sigma models and other continuum two-dimensional field theories. So one can ask how to see these two-dimensional continuum field theories by studying this four-dimensional gauge theory. So suppose we had a very fine lattice with lots of Wilson lines here and lots of Wilson lines here, which were orthogonal. Then when we integrate out the gauge fields, if we have a large number of Wilson lines, they're parallel at different values of z. When we integrate out the gauge fields, we find a lattice, a very fine lattice. So to take a continuum limit of a lattice model, we should replace this very large number of parallel Wilson lines by a continuum of Wilson lines, another continuum of Wilson lines here. That continuum of Wilson lines will now be a surface operator instead of a line operator. So the idea is that one should be able to see two-dimensional continuum theories by inserting surface operators at two different points, and then they will exchange gluons. And that should give us some integrable 2D continuum theories. So let's see how this works in practice. Oops. So one way to describe at least some class of Wilson lines is to write them in terms of by coupling my gauge theory to a quantum mechanical system. So here we're going to take the gauge group to be SU2, and I'm going to couple to a quantum mechanical system, which is just topological quantum mechanics in the cotangent bundle of CP1. So there's a field which is a map to CP1, another field which is a function valued in the pullback of the cotangent bundle of CP1, and just a GDF action. Now, the reason for choosing this, if you think about what Wilson line this will lead to a certain infinite-dimensional representation. The reason for choosing this particular way of writing a Wilson line is that it admits it's easy to see how this should extend to write a continuum of Wilson lines. Suppose I had a Wilson line at every value of y living in the x direction. Then, for every value of y, I should have such a map to CP1. But that's just a map from R2 to CP1. Sorry, that cotangent bundle should not be there. That was a mistake. So a map from R2 to CP1. And then I should have some other field, G, which is a section of the pullback of the cotangent bundle. And an action, which is the same kind of action, GDF, together with the dy term, because now we're summing over all the different positions, the continuum of the positions of the Wilson lines. Now, if you think about what this theory is, after you Wick rotate, this is just a beta-gamma system. In this theory, the fields only propagate in the x direction. And similarly, if we wanted to put a continuum of Wilson lines at a different value of z, we would get a beta bar gamma bar system after Wick rotation. So before Wick rotation, you would have a theory where fields only propagate in the y direction. And let's think about what this looks like after this Wick rotation. We've just coupled to a beta gamma system at z0 and a beta bar gamma bar system at z1. And of course, the beta gamma system has a chiral anomaly, as does the beta bar gamma bar system, but this is cancelled by introducing a Chern-Simons term, which is integrated over a 3-manifold which ends on each of these surfaces. Now, if you think about what happens when we integrate out the gauge fields, the exchange of gluons, the exchange of a single gluon will lead to this beta-beta bar term. that is nothing but, well, if you take a beta gamma system and a beta bar gamma bar system and add on beta beta bar interaction, well, that is nothing but the actual physical sigma model on CP1. So the picture is, here we have a chiral theory, here we have an antichiral theory. They exchange gluons, which leads to a full two-dimensional theory. Now, so this is a mistake. This should not be 1 over. The distance between them is proportional to the volume. So as these surfaces get very far apart, we're taking the large volume limit, and the theory decouples into chiral and antichiral theory. But another aspect of this story is that one can see, for completely formal reasons, why the CP1 model is integrable. What do? So you insert a Wilson line at some other point, and once we integrate the gauge fields, this gives a current in the two-dimensional system. Now these Wilson lines, for the same reasons we discussed before, all commute with each other for every value of W. So now we find an infinite number of commuting currents, so the theory is integrable. So this is a mechanism for producing a very large number of two-dimensional integrable systems. So let me mention some systems we can produce. This is my last slide. Well, we can put in a beta gamma system on some homogeneous scalar G manifold, X, but we need to cancel the anomaly of the beta gamma system. We need the P1 of X is 0. And this will give us the sigma model on X if we have a beta gamma system and a beta bar gamma bar. So as an example, we can do the sigma model on flag varieties. But one cannot see the CPN model in this way, because CPN, when n is bigger than 1, does not have vanishing P1. So if one tried to do this with CPN, we would find that there was an anomaly which could not be removed. One can, however, see the supersymmetric CPN model. So another fun class of examples one can study is, instead of inserting a bosonic beta gamma system, we can insert a fermionic system at Z0 and an antichiral. So a chiral fermion at Z0 and an antichiral fermion at Z1. And if you calculate what happens when they exchange gluons, you find the Thirring model. And again, you see formally why the Thirring model is integrable. Okay, so I'd like to stop there, and thank you for your time. I don't think so, because then the Wilson lines are kind of forced to stay at a particular value of z. Otherwise, well, there is only one of the components of the connection in that direction. Another way to see this is that these theories arise as a twist of certain supersymmetric theories, and only the Wilson lines are only supersymmetric if they go in some directions.
Any other questions?
So can one also describe long-range integrable systems through this Chern-Simons description? And also, even in the nearest neighbor one, there's always quantum deformation, which includes long-range interaction.
I don't know. I think I don't know the integrable systems literature well enough to understand these models. So.
So can you do it for the topological twist for n equals to 4, and is it going to give the same thing or different thing?
I mean, like studying Wilson lines and a topological twist of n equals 4?
Yeah. Because in n equals 4, we have two different twists, right?
Well, what you want to do for n equals 4 is not take a topological twist, but take a twist introduced by Kapustin, which is partially topological and partially holomorphic. And it turns out if you take a D3 ray and transverse to a tab nut, and you do this twist, you find this model, but for a certain supergroup. So
Okay, I think there are no more questions. Let's thank everybody.